Find the intervals over which each function is differentiable and continuous. So this is pretty similar to what we had done back up here where we're finding the intervals over which it was differentiable. And I went ahead and compared it to the domain. We're going to do the same thing again. For some reason, I don't know, maybe there's a reason. We'll see. We'll see how this thing plays out. All right, so I've got on number 1, I've got a quadratic function. It has no sharp turns. It has no vertical tangent lines. It has no discontinuities. This is differentiable everywhere. So for diff, it's all real numbers. And its domain is also all real numbers because it is polynomial. Because we said, hey, polynomials are continuous everywhere, so it's all real numbers. And we can see that those two things are exactly the same. Wherever it was defined, it had a derivative at that particular point. Okay, and then over here on the absolute value graph for the 4,000th time, it's differentiable everywhere except the origin because you have a sharp turn there. So it's differentiable negative infinity to 0 and then 0 to infinity. But where is it defined? Its domain is everything because, hey, you have a sharp turn at the origin, but it's still continuous there. Domain is all real numbers. And as I mentioned before, this, where it's differentiable, this interval is a subset of the domain of that particular function. And we can say back over here the same thing is true, is that this set fits inside that set. It just fits very comfortably, like, you know, 1-to-1. All right, but back over here, what we're saying is just because it's defined at every single point, just because it's continuous at every single point does not necessarily mean it's differentiable there, which is going to lead us to a super important theorem in calculus, which the title itself is pretty much the theorem. Differentiability implies continuity. And so the actual statement here is if f is differentiable at x equals a, remember that means that you can take the derivative there, the derivative actually exists, then it is continuous at x equals a. It's an if-then statement. So the first part, the condition that must be satisfied here is that your function is differentiable, and then we can conclude that it's continuous at that particular point. So look over here at this absolute value graph. Where is it differentiable? It's differentiable on this left-hand side, so therefore it's continuous there. It's differentiable on the right-hand side, therefore it is continuous. Right? And then the same thing over here on this piecewise function. It is differentiable on the left-hand side. It's just a line. It's just a horizontal line. It's constant. And so the derivative would exist there. It is differentiable on the right side of the origin, and so it's differentiable there. Let's look at this in reverse. Remember, you can take an if-then statement, and you can take the converse. You can flip it around. Right, the converse and the contrapositive of the theorem below. It's the same theorem that we were just talking about, and determine the truth value of each statement. Well, it sounds like we're in geometry again. I hope this does not induce any kind of anxiety or nightmares. Let's see, let's add a page in here. Converse. Oh, well, here, let's kind of a recap here. This is what an original if-then statement looks like. P implies Q, where the P is the if part, Q is the then part. Converse. Remember, you just switch that thing around. You switch the if and the then. It's Q implies P. But then I also wanted us to do the contrapositive here. So contrapositive, you flip it and you negate it. It's not Q implies not P. Right? Okay. So I'm going to take the converse of this particular statement. You might remember from geometry, when you have an if-then statement, its converse is not necessarily true. That's what we're going to take a look at. So the P part is differentiable. The Q part is continuous. If f is continuous at x is equal to a, then it is differentiable at x equals a. Is that true or is that false? This is the converse here. Converse. Just because it's continuous, does it have to be differentiable there? Well, we've got an example right here that showed that that was not the case. It is continuous. This function, this absolute value function, is continuous everywhere, but the derivative does not exist there. Sharp turn. That's our counterexample to show that this thing is a big fat false. And we can just look at an absolute value graph and show right there, there's the counterexample. That is not the case. So it's pretty important for you to understand that just because your function is continuous does not mean it's differentiable. However, if it is differentiable, you know it must be continuous at that particular point by this theorem. As a matter of fact, on the AP test, they won't tell you that a function is directly continuous. They will instead say that f is differentiable. And then I'm going to use this theorem to automatically conclude that it's continuous. Okay, I'm trying to get the eraser, guys. F is continuous. And it's important because many times on the free response question, you're having to apply one of the theorems, and that theorem could be the intermediate value theorem or something like that, which one of the conditions, one of the initial conditions is that it has to be continuous. And you have to state it. If it says differentiable, you need to go an extra step and say that it's continuous because of that. All right, let's look at the contrapositive. Contrapositive, I'm going to flip and negate it. Do you remember the relationship between an original statement and its contrapositive? Anybody? I hear nothing but silence. All right, so we're going to flip and negate it. If f is not continuous at x equals a, then f is not differentiable at that point, at x equals a. If it's not continuous, it can't be differentiable because that's one of the places where our derivative fails to exist. I'll just scroll up here. I'll make you dizzy for a second. It's right there. Discontinuities, that's where a derivative fails to exist. And so this one is a true statement. If you're not continuous, you're not going to be differentiable. So it's a big fat true. So yeah, back from geometry, contrapositive and a given conditional that it comes from, they're logically equivalent to each other. It means that they have the same truth value. All right, so that about wraps it up. But hey, I hope that you wrote something down for this. Continuity implies, no, differentiability implies continuity. It's going to come up maybe once or twice the rest of the year.